Hello dear viewers, welcome to another Geonodes Daily series tutorial where we do something cool in geometry nodes and we learn something interesting about how to use those awesome nodes that are now part of Blender. And this demo from today will help us try to better understand how the rotation works, something that I still find scary after using Blender for a few years now. I still find it scary because the results are oftentimes hard to predict because of a few things that we will deal with today. So as you can see from the curriculum, this is what we will try to achieve today. A little bit of explaining the rotation and all that good stuff. If you want to see the materials, there will be a video dealing with that. Today we will look at geometry nodes. And as usual, I want to give a big thank you to all of you that are supporting this channel. Thank you for subscribing, liking the videos, commenting on them. That helps the YouTube algorithm pick up the video and show it to more people. And a special thanks for all of you that are deciding to purchase these project files from Gumroad. It's helping this channel keep moving on, and also you get something cool to play with. So going to the first point, first let's build something interesting to look at, the thing in the demo, and then we will see what we can say about rotations. I want to instance something on our scene. We will need some points, and that will be our circle. So let me plug this one into the instance, and what we want to instance will be, in this case, a cube. We'll try to keep things simple. And right now we have a huge scale, so let's make those smaller. And now we kind of have what we want. First things about rotation. I want to align this properly. As you can see, right now everything is following this line, the way the cubes were instanced at the beginning. This is how they look, and they keep their position rotation, regardless of the position. So in order to fix that, I'm going to take and align Euler to vector. So given the position of these ones, it doesn't matter if we use this axis or this one axis to align, because this is what we get here, the axis to align. So let's choose Y. And now if we start to play with these values, you can see we can control the alignment of this thing. But we also have a field input that we can plug something into it. So let's take the normals. And that allows us to align each instance based on the normals of the circle. And this is what gives us this result. We can align the Y or the X-axis to the normal, and we get this result. If we push to Z, then this is something completely different. But that's not the only thing that I did in the demo. I want to turn this into wireframe. And that's kind of easy with the geometry nodes. First, we want to change this into a spline, a curve, and now we get this that we of course can't see in the render, so we have to turn it into a mesh. So now having a curve, we can turn that back into a mesh and give it some substance with a profile, like this circle from here. We can plug it here and we get this jumbled mess. One thing that we want to change is the thickness of the wire, and the other one, the resolution, because we don't need so much resolution. So now we have this nice setup that we can play with, and that takes us to the second point of rotations. Having instances output from here, let's do a rotation of those instances. I'm going to plug this one here. And if we play with this value, we can see something happening. I'm choosing Z because this way we are basically rotating around the pivot point of our geometry in a way that it's easy to see here. As you can see, this is local space. That means we take the pivot point of each of these instances, and in that this case it will be the origin that we have it right in the center of the object. So if we look at this, each point has an origin, each instance has an origin, and we can rotate around it like this. If we start to play with this pivot point, so let's say I'm putting it like this, what is happening basically, it's instead of taking, let's go to the first frame and cancel, instead of taking it from here, where is the origin, we can push the pivot point, meaning we are basically moving this point something like that, and actually not like that, don't have to have a meter to have like that. And now we can do a rotation around that for each instance. What happens if we uncheck this box? We are talking about local space, not local space, but world space now. That means we move everything together. And again, if we play with this value, we are changing, instead of rotating around the 0, 0 point, we are rotating basically around this point. So now we can have something like this, as you can see. And if we put this 0.5, we are basically putting the center here, and we start to rotate around it like that. So that will be world space versus local space affecting the rotation. Another way to affect the rotation, if we are in local space, is, let me reset the pivot point. Right now we rotate simple around this origin, but if we push this one here and we change the pivot point here, the location of the geometry, by taking a transform node and plugging it here, and let's say we put a translation of 1 here, meaning we still keep the origin in place, but we change the geometry, as you can see here. Now if we start to play with this value, as you can see, we get this result because we are basically pivoting around the point that it's further away like this. Not that much, like I put it, something like this. And we get this result. And if we change the pivot point here to 1 meter, what we basically did was cancel that movement. So we are back at this point because this is responsible for pushing the geometry out from the pivot point, and this one is responsible for putting it back. The concept is not complicated, but it takes a while to wrap your hand around it and to predict the movement, because as you can see, we get some parameters here, the so-called rotation here, and we can choose if we want to rotate everything around the very individual pivot points, or if we want to rotate the whole thing. And in both cases we can change the pivot point and getting all sorts of different results, as you can see here. And that's just by playing with simple values. But what happens if we change all the axes? Or what happens if we change the pivot point in strange ways? So let's say that we take the position and we plug it here. What will happen? Now we change the pivot point for each instance based on its position in the 3D space. So now we get results like this. And if we switch from local space to world space and we play with this, well, now they are acting like we are working in the local space, because we are basically, this is what we do. Now we pivot around each instance position. And what happens if we play with this even more? So let's say I take a vector math and switch it to some function here, like sine. And now we start to play with this. You see, we get different results. And if we play with another function, let's say cosine, and we plug this one here, well, we get a completely different result. And like I said, this is what makes it hard to work with, because they are not so easily to predict. And that's why I still get scared by rotation and I find them complicated. But if we take it step by step and we do things visually, like we did here, they are not so scary anymore. And you can get cool results, as you can see. So what I want to do for the next point is to build some logic that will help us switch between this output and this output for the pivot, and between local space and world space from here. So how can we do this? One thing, so let's say we have a rotation like this, and we start to play with this value. If we want to switch between these, as you can see, we don't have a seamless transition because we have a rotation. If we cancel this rotation, we can now play with these values. Or if we go one full revolution, as you can see, we can switch between these no problem. But as soon as we have ever so slightly change in value, you can see it here. So if we want to get a seamless transition, we must make sure that this will happen only at full revolutions of this circle, 0, 360 degrees, or times 2 that, 7 to 120 degrees, and so on and so forth. Now we can play with these values, but only at full revolutions. So this is the cool part. We will build a series of switches that will help us switch between this one and this one outputs, and between this one and this one. So let's animate this first. And for that, I'm gonna take a scene time node, and because I want to control the speed, I'm gonna do a division here on this one, let's say like 20. And watch what happens when we put this into the rotation and do world space. We get different result than before, because basically what we are doing is pushing this singular value to all three values here. So we get this instead of just playing with one value. Of course, you can make this even more complex by doing offsetted rotation for each axis, but I think it's complex enough. Now, the way to switch between this animation at full rotation is to take this value and compare it with 360 degrees, basically. So we want this output, and we want 360 degrees in radians. And that's gonna be, if we put a value here, we have pi times 2. That's gonna give us 6.2 something. That's one full revolution, 360 degrees in radians. We need to use radians here. And now basically we have a switch that says, okay, if we have a value that is greater than one revolution, we do something. And what do we want to do for this? Well, we want to switch between sine and cosine. So if we want to switch, let's take a switch this one to vector, give it this condition, and we can plug this one here and this one here. So now if we push this into the pivot point, depending on the speed, it will happen faster or slower. but we will start by using one animation, and at some point, after one revolution, we will switch to the other animation, as you can see here. Excellent. What I want now is that after one revolution, I want to wait for another one. So let's duplicate these nodes and say, okay, we have one revolution here, but if we add one more revolution here, so let's say I want to add one to, sorry, so I take this value and I say I have two revolutions. If I have two revolutions, I want to switch from local space to world space. So plug this one here. That means we start the animation. We have one revolution. When we get to the second revolution, we start to have this switch from sine to cosine. And when we pass two revolutions, we get into the third one. I'm having the cosine animation, but instead of using one space, I use the other. Instead of using the world space, I switch to local space. So I get this result now. But after this, I want to switch again the animation. Instead of having the cosine, I want to have the sine. So how can we do that? Well, let me duplicate this node and say like this. We have this revolution, but after 3 rotations, I want to have another switch that will control this pivot point. So how do we want to do the switch? Why did I still keep this one here, even though I only changed the pivot point here? Because I want to start by having a sine in this local space, world space. Then I want to have a sine in local space. Then I want to have a sine in world space, and then I want to have a cosine in the local space, basically for animations. So in order to keep this being a sine, even though we change the spaces, I want to take the output of this one to plug it here, and then I want to take the sine and plug it here. So that means that after one revolution, this will switch from sine to cosine, but passing the result through here means that even though the output of this one will be the cosine function, because we are still using this, that means that when we finish 2 revolution, we will take the output from the true value. Between 1 and 2 revolution, we will use the output from here. That will be either sine or cosine. And when we pass 2 revolution, we will use the output from here, that is hard-coded to this sine function. So now we can take this output and plug it here and say, okay, after the third revolution, I want to switch this from sine that I'm using here to cosine. So that means I'm going to push this one, take this one and push it here, and actually use this output here. So what I did is I changed the animation. I said, okay, we start. For the duration of one revolution, I want to use the sine function. Because this is not greater than 1 revolution, I'm going to use the sine function. And because we are not greater than 2 revolutions, I'm going to use the world space. After one revolution has passed, this becomes true. So I'm going to use the cosine function. So between because this one also gets true, I'm going to use not the cosine function that is output here, but the output from here that is actually my sine function. So I just switch from world space to local space, but I'm still using the sine function. But after two revolution, when we get to the third revolution, what happens? I'm taking the output of this one, that it's already true because we are creating in two meanings we have a sine, and I'm passing it here. So I start by using this output, that in this case is actually the sine output, for as long as we are less than 3 revolutions. But when we are greater than 3 revolutions, I'm using the true output from here that I decided that I want to be the cosine. So this is how I cascaded the animation. I changed them and got like from sine on the world space, I switched to sine on the local space, and then from sine in the local space, I switched to cosine in the world space. So we got the 4 chained animations. And in order to make things a little bit easier to follow, I'm gonna show you now the cleanup node tree, so you can take some screenshots. So this is how the cleanup node tree looks like. And this is how our animation looks like with all the bells and whistles. And looking at this, we generated our circle of cubes here. Cube, change the pivot point for it, and then playing with the geometry to get a wireframe. I aligned everything to the normals, and then we started doing the logic here. This is the animation part. We control for speed, and of course we have our constant 1 revolution, and we switch between sine and cosine. First switch, second switch, and the last switch, giving us 4 distinct animation, of course attaching also on material. And I exposed these parameters, so you can what I did extra here, I exposed these values, take the revolution, 1 rotation, and say how many rotations do I want to have the first cycle. In order to change them, I said, okay, add the first cycle rotation length with the second cycle rotation length, and then take this output and add the third cycle rotation length. So if I change this to 2, everything will still work, but the first stage will be longer. If I change this one to 2 or whatever value, the same it will work. Even though I change this one, we are still going to chain seamlessly without no problems. That's why I did things this way. As you can see, start this length multiplied by 1 is going to give us 1 in this case. Then adding this one with this one will be 2 multiplied by the rotation, meaning 2 rotations. And whatever the result is so far, we are going to add the third length, and in this case it's going to give us 3 rotation or whatever we change these values to. And this is giving us the result that you see here. Thank you very much for watching. I hope I managed to share some light on how you can play with rotation in world space, local space, what's the point of the pivot, how you can change the relation between the origin of the geometry and its rotation point where the real geometry is, and how these things work. With practice, being